Let's look at integrated rate laws. So integrated rate laws expresses a reactant concentration as a function of time given the differential rate law. Okay, so we shall proceed by looking at a reaction involving a single reactant. Reactions involving a single reactant. Okay, so we have air forms products. So the rate law, the general rate law for this reaction will be negative delta A over delta T, which is equal to K A to the power n. Okay, to the power n. So we will develop the integrated rate laws individually. Okay, so these rate laws will be developed individually in cases whereby when n is equal to 1, that is first order. When n is equal to 2, second order. When n is equal to 0, that is zero order. Okay, so we start with the first order. So let's look at first order reaction. First order reaction. First order, so we call it first order rate laws. Okay, so we look at first order rate laws. So consider for the reaction nitrogen pentoxide, so this one is in solution form, forms nitrogen dioxide plus oxygen. So nitrogen dioxide also in solution form plus oxygen gas. Okay, so this is the decomposition. Okay, so we can write the rate for this reaction. Okay, so rate will equal to negative delta N2 O5 over delta T, which is equal to K N2 O5. Okay, that is for a first order reaction. Okay, so since the rate of this reaction depends on the concentration of nitrogen pentoxide to the first power, it is a first order reaction. So that is first order reaction. Okay, since n is equal to 1. Okay, so this means that if the concentration of nitrogen pentoxide is doubled, if the concentration of N2O5 is doubled, the concentration of nitrogen, the concentration of nitrogen dioxide and oxygen would double as well. Okay, so if you double the concentration of the reactant, the concentration of the product also doubles. Okay, so now we can write the integrated rate law for this reaction. So the integrated rate law for this reaction would be ln Ne2O5 is equal to negative Kt plus ln Ne2O5 initial. Okay, so where the ln is the natural, this is the natural logarithm. Okay, it's the natural logarithm, the ln. So we can write the general equation, for a chemical reaction that involves a single reactant. So consider a reaction involving a single reactant. A forms products. Okay, A forms products. So the rate of this reaction, so rate is equal to negative delta A over delta T, which is equal to K to the power K times concentration of A. Okay, then the integrated rate law, would be ln A is equal to negative Kt plus ln A initial. Okay, so this is the general integrated rate law for a first order reaction. Okay, so there are some points that we can take note. We can note about this equation. Okay, so ln A is equal to minus Kt plus ln A initial, the integrated rate law for a first order reaction. So there are several important things to note about this equation. Okay, so the first one is that the equation shows how the concentration of A depends on time. Okay, it shows how the concentration of A depends on time. Okay, it shows how the concentration of A depends on time. So if the initial concentration of A and the rate constant, if the initial concentration of A and the rate constant K are known, the concentration of K can be calculated at any time. Okay, so once A initial is known, K is known, then we can calculate the concentration of A at any time t. Okay, then the second point to take note is that the equation is of the form. The equation is of the form y is equal to mx plus b. That is the equation of the straight line. Okay, whereby we know that a plot of x or a plot of y, this is x, gives a straight line of slope m. So in this case, y is equal to ln A. Y is equal to ln A. Then m is equal to negative k. Then t is equal to x. Then b is equal to ln A initial. Okay, so it means that a plot of ln A, this is t, gives a straight line. gives a straight line. A plot of line A, this is T, gives a straight line, okay, with the intercept line A initial. Okay, so this is often used to test whether this fact is often used to test whether a reaction is first order. Okay, so if you have a plot of line A, this is T, and you get a straight line like that, it means the reaction is first order in A. Okay, so that's the conclusion. So we need to get a straight line. If it's not a straight line, then it's not a first order reaction. Okay, then the other point that we need to take note of this equation is that the integrated rate law can also be expressed in terms of the ratio. Okay, we can express this equation. We can express the equation, this integrated equation in terms of the ratio. Okay, since we have line A, which is equal to negative kt plus line A initial. Okay, so we can write this as a ratio. So what we do is we can transpose negative kt to the other side, then this side, then line A goes this side. Okay, so we are going to have line A initial minus line A is equal to kt. Okay, is equal to kt. Then now since we are subtracting the lines, so this is the same as line A initial over A is equal to kt. Okay, so that is the ratio. Okay, so we can use this. We are going to use this ratio also to derive some important equations that we are going to use later on. Okay, so we look at the example. So let's have an example. Let's see how we can use the data to verify whether the data is for a first order or second order reaction or zero order. Okay, so we are going to look at the decomposition of nitrogen pentoxide. So the decomposition of nitrogen pentoxide, which gives nitrogen oxide plus oxygen gas. Okay, so the results, the decomposition of nitrogen pentoxide, gave the following results. So these results were corrected. Okay, so let's see how the results are looking. Okay, so we have the concentration of nitrogen pentoxide, then we have time in seconds. So the time is in seconds. Then now the data that we are collected. So the concentration is 0.1, 0.100, then we have 0.0707, 0.05, 0.05, 0.0025, then we have 0.0125 and 0.00625. Okay, then the time is 0, 50, 0, 50, 100, 200, then 300 and 400. Okay, so these are the results obtained from the decomposition of nitrogen pentoxide. So the question now is using this data, verify that the rate law is first order. Verify that the rate law is first order in N2 or O5 and calculate the value of the rate constant, and calculate the value of the rate constant K. Okay, so this is the information. So now in order for us to calculate in order for us to verify whether this data is for first order reaction in nitrogen pentoxide, we need information on we need to have the information on lean concentration. This is time. Okay, so we shall need to plot a graph of lean concentration. This is time. So what we need to do now is to find the lean concentration. Okay, so natural logarithm of 0.1, it's giving us negative 2.30303. So lean is 0.07, you get negative 2.649. Then the other one will be negative 2.996, negative 3.689, negative 3.689. Then we have negative 4.382. Then lastly, lean 0.00625, it's giving us negative 5.00775. Okay, then the time remains the same: 0, 50, 100, 200, 300, then 400. Okay, so you need to generate a table like this one. You find the lean concentration. Then now on your graph paper, you are going to plot these values. Okay, so we can use this space here. Okay, so we plot these values. Okay, on the graph you are going to draw a graph of a suitable scale. Okay, so here on the y-axis you have lean N2, lean N2O5. Okay, so on the x-axis, on the y-axis is the concentration, then on the x is time. Okay, so our time runs from 0 to 400. So there you are going to make a good scale. Okay, you make a scale on your graph. Okay, so you can have 0, 100, 200, then 300, then 400, not drawn to scale. Then y-axis, we have these numbers which runs from, so we can have a scale of -6 up to 2. Okay, so suppose we have a -6.0 here. Okay, you can start with -6, then here we can have -4, -4, -4, then here -2. So this is line N205. Okay, so this is the scale. Okay, so 6.0, 4.0, then -2.0. Then now we plot. So 0, -2.3. Okay, so you can have it somewhere there. Then we plot 50, -2.6. Then we plot 50 somewhere there. Okay, then we have 200, 3.3 something, 3.689. So 200 is somewhere here. Then we plot 300, 4. Since this is not drawn to scale, okay, so we are just estimating. Okay, then 400, 6. So you can see here, somewhere here. Okay, so you can see how it's coming out, not drawn to scale. So now you join these lines, these points, you join the points, so you can see it is giving us a straight line. Okay, so when you do it on the graph paper, you see clearly. Okay, so since a plot of line N2, since plot of line N205 versus T gives a straight line, so the reaction is first order. The reaction is first order in N205. Okay, so that is how you verify. Okay, so the reaction is first order. Then now let's calculate the value of K, the rate constant. Okay, so how are we going to calculate the rate constant? So to calculate the rate constant, since we know that slope is equal to negative K in this case from our equation. So now we know that slope which is equal to change in y. Okay, slope is equal to delta y over delta x. So in this case, our delta y is line N2, delta N2 over delta t. Okay, so that is our slope. Okay, so or you can write it like this. You can put the delta outside the brackets. Okay, so that is the delta y, delta line concentration N205. Okay, you can put the brackets, it's all the same. Okay, so means that slope is change in y over change in x. Change in y, we have the line. Okay, then delta. So to calculate that, we simply pick the first and the last points. Okay, since the first since the first and the last points are exactly on the line, we will use these points to calculate. So we're going to use negative 2.03 and this one. Okay, so which is just, you can pick any points, but since these are exact on the points, they'll give us an accurate solution or answer. Okay, so slope in this case now, slope will equal to negative 5.05 minus 2.303, then over time is 400. You can see here it's 400 seconds minus 0 seconds. Okay, so which will now give us it will give us a slope of negative 6.93 times 10 to the power negative 3 per second. So this is our slope. Okay, then K, remember slope is equal to negative K, so K now will equal to 6.93 times 10 to the power negative 3 per second. So that is how we can calculate. Okay, then we can now look at the half-life. Let's look at the half-life. So half-life of a first order reaction. Half-life of a first order reaction. Half-life of a first order reaction. So the time required for a reactant to reach half its original concentration is called half-life. Okay, so time required for a reactant to reach half its original concentration. Its original concentration is called half-life. And is designated by T half. Okay, so that is how we define half-life. Time required for a reactant to reach half its original concentration. That is what we call half-life, T half. Okay, so now we can derive. Let's derive the formula for calculating half-life. So we can derive the formula from the integrated rate law of first order reaction. Okay, so remember that the integrated rate law is ln A is equal to minus KT plus ln A initial. So the ratio is A initial over A. Remember, we derived this ratio earlier on, which is equal to KT. So from this now we can derive. So by definition of half-life, so it means T is equal to T half. T is equal to T half. Then A is equal to A initial over 2. Here time required for a reactant concentration to reach half its original concentration, which is here now. Okay, so you divide by 2 since it's half. Then now we substitute in the equation. So we are going to have ln A initial over A is A initial over 2. So here A initial over 2. A initial over 2. Okay, which is equal to K, T is equal to T half. So it comes to this. Okay, so we can sort out what we have in the brackets. So you can see clearly that A initial will cancel. Okay, so we have A initial over A initial. These will cancel and we shall remain with a 2. Okay, so this one now becomes ln 2, which is equal to KT half. To show you how these are cancelling, since we have A initial divided by A initial over 2. So you can see. So this one now becomes A initial times 2 over A initial. Then the A initial will cancel, leaving ln 2 there. Okay, so we make T half the subject of the formula. So T half-life is equal to ln 2 over K. Okay, ln 2 over K. Then what is ln 2? So ln 2, that is 0.6. Okay, so half-life of first order will be 0.693 over K. Okay, so this is the formula that we shall be using to calculate the half-life of the first order reaction. Okay, so this equation can be used to calculate K. If half-life is known, or to calculate the half-life is if K is known. Okay, so note that for a first order reaction, the half-life does not depend on concentration. Okay, so T half for a first order does not depend on concentration. Okay, so half-life of a first order reaction does not depend on the concentration of the reactant. Okay, so let's see how we can use this equation to solve some problems. Okay, example. So a certain reaction, a certain first order reaction has a half-life of 20 seconds. Okay, has a half-life of 20 seconds. So question A, calculate the rate constant. Calculate the rate constant K. Calculate the rate constant K. Then B, how much time is required? How much time is required for this reaction? For this reaction to be 75% complete. Okay, so we can solve solution. So we know that for a first order reaction, half-life is given by T half is equal to 0.693 over K. Okay, so now we calculate K. Let's make K the subject of the formula. So K is equal to 0.693 over T half. Okay, so 0.693 over T half. So the half-life of this reaction is 20 seconds. 20 seconds. 20 seconds. So now you divide that number. Okay, so when you divide, you are going to get K is equal to 3.47 times 10 to the power negative 2 per second. Okay, so that is the value of K. That is the value of K. Then now let's solve the second question. How much time is required for this reaction to be 75% complete? Okay. B, we can use this space. So if the reaction is 75% complete, if it is 75% complete, so it means 75% of the reactant has been consumed. So it means 75% of the reactant. 75% of the reactant has been consumed, leaving 25%. Leaving 25% in the original. Okay, leaving 25% in the original. Okay, so that's the meaning. 75% of the reactant has been consumed, leaving 25% in the original. So this simply means A over A initial times 100% is equal to 25%. A over A initial over 100, A over A initial times 100% is equal to 25%. 25%. So this means this one, if we divide by 100 this side, so this one is the same as A over A initial is equal to 1 over 4. 1 over 4. Okay, A over A initial is equal to 1 over 4. Okay, so means that if we interchange this, the A initial on top, this one down, so it means now A initial over A is equal to 4. A initial over A is equal to 4. Okay, then from the integrated rate law, we know that we have ln A initial over A is equal to KT. So we know this one. Okay, so which is now equal to A initial over A initial over A is equal to 4. Okay, so we simply put a 4 here. 4 is equal to KT. K, we found our K, which is 3.47. 3.47, okay? 3.47 times 10 to the power negative 2 per second. Okay, then it T. Okay, then now we calculate T. Okay, so T now, it means T is equal to ln 4 over 3.47 times 10 to the power negative 2 per second. Okay, so you do that, you calculate ln 4, then you divide. So you are going to find t is equal to 40 seconds. Okay, so that is our t. That is our t. Okay, so even when you use another method to say maybe you start with 1.0 molar. Okay, after one half-life you are going to remain with 0.5. After another half-life it will be 0.225. Okay, so the half-life of a first order is it's constant. Okay, it's constant. So now, so if it takes so like from 0.1 to 0.5, so it means here 50% used up. Okay, so it means 50% is gone. 50% is gone. So another half-life after one half-life has gone, so after one half-life the reaction has consumed this 50%. Okay, 50% to completion. 50% to completion. So now after one more half-life would give this 0.225. okay, 0.25. so now if we compare, so it means now it is it will need 0.25. I mean it will need 2 half-lives. So it requires two half-lives to have 0. So that this one remains. Then now the half-life of the reaction is what? 20 seconds. So you just do 2 times 20 seconds, which is giving us 40 seconds. Okay, that's another way. All right, so that is how we can determine. So now let's look at second order reaction. Second order rate laws. Second order rate laws. Okay, so for a general reaction involving a single product, a single reactant, for a general reaction involving a single reactant forms products. So the rate will equal to negative delta A over delta T, which is equal to K to the power 2. Okay, so that will be the rate for a second order. Then now we do the integrated. Okay, so the integrated rate law for second order reaction, it will be so we integrate now this equation. Okay, so we are going to have 1 over A is equal to KT plus 1 over A initial. Okay, so this is the integrated rate law for a second order reaction. Okay, so we can see clearly that this reaction, this rate law is of the form y is equal to mx plus b. So in this case, our y is equal to 1 over A. Okay, 1 over A. M is equal to K. Okay, T is equal to X is equal to T. Then B is equal to 1 over A initial. So it means that a plot of 1 over A. A plot of 1 over A, this is T, must gives a straight line. Okay, so if you plot 1 over concentration, this is T, and you get a straight line, that is, it means the reaction is second order in A. Okay, then half-life of second order, reaction. So the half-life, we do the same. We use 1 over A KT plus 1 over A initial. Okay, so if we substitute by definition, so by definition, T is equal to T half, then A is equal to A initial over 2. Substitute into the equation. So we are going to find the half-life of second order reaction as half-life is equal to 1 over K A initial. Okay, so this is the equation for half-life of second order reaction. Okay, so now let's have an example. Let's see how we can solve a question involving second order. Okay, so the following reaction, we shall look at butadiene. Example, we look at butadiene. Butadiene reacts to form its dimers. Okay, butadiene reacts to form its dimers. According to the reaction. C2H6 then forms the C8H12. Okay, so the following data were corrected. So we have the concentration of butadiene, HC4H2, then time in seconds. So we have 0.000, okay, 0.0625, 0.00476, 0.00370, 0.00313, then 0.0000241, then 0.00208. Okay, then the time 0, we have 0, 100, 1000, then 1800, 28, 36, 440, 00, then 5200. Okay, hope we have not left out one figure. Okay, so let's see. So we have 1 2 3 4 5 6 7. So we left out one figure this side. Okay, on the on the concentrations. So the first one is 0.01, okay, 0.00625, then 0.00476, then we have 0.0037, okay, then 0.00313, okay, then we have 0.0027, okay, so it's here. So we have 0.00270, then 0.00241, then 0.00208. So time 0, 1000, 1800, 1800, 2800, okay, then 36, 4000, 00, 4400, 5200, then 6200. Okay, so this is a full table. Okay, so these are the results. Then now the question is verify that this reaction is second order. Verify that this reaction, verify that this reaction, verify that this reaction is second order in C4H6. That's question A. Then B, what is the half-life? What is the half-life? What is the half-life? What is the half-life of this reaction? What is the half-life of this reaction? Okay, so these are the two problems that we need to sort out. Okay, so now to verify that the reaction is second order, we need to plot a graph. Remember, we need to plot a graph of 1 over A, this is T. 1 over A, this is T. That should give us a straight line. Okay, a graph of 1 over A, this is T, should give a straight line. So in this case, our A is C4H6, the butadiene. So we need to have 1 over H4. So we find the inverse concentration. Okay, then we have time this side. Okay, so we are going to have concentration. This is time. Okay, so now we find 1 over concentration, 1 over this 1, so it will be 1 over 0.01. we get it's giving us 100. Then we do the same here for all of them. We find the inverse. Okay, so the first one is 100, then 160, 210, then 270, 320, 370, 415, and 481. Okay, so that is the inverse concentration, 1 over concentration for each. Okay, then it, of course, time remains the same. Okay, so we have 0, 1000, 1800, and then 2000, 800 3600, and then 4400, 5200, then we have 6200. So this is the table, okay, 1 over concentration. Then now we plot a graph. So we are going to plot a graph of we are going to plot a graph of 1 over C4H6. Okay, this is T. So T runs up to 6,000. Okay, so we have 0, maybe 2,000 here, 2,000, 4,000, 4,000, then 6,000. So you come up with a scale. Then concentration is 100 to 480 to 481, 100 to 481. Okay, so 0, so maybe 100, 200, 200, then 400, somewhere there. Okay, so now we plot these points. Okay, so we have 0, 100, 0, 100 there. Okay, then 160, 1000, 160, 1000, then 1000, 160, so 1000 is here, 160 somewhere here. Okay, then we come to 18 goes to 2000, 210 somewhere here, somewhere there, then 6000, 4 somewhere there. So you can see it is giving us a straight line of positive gradient. So you can do that on your graph paper, you get defined points. Okay, so we have verified. So the reaction is second order in C2H6. Okay, then now let's determine the rate constant. Let's determine the rate constant. I mean the half-life. Okay, so the second question is determine the half-life. Determine the half-life of this reaction. So to determine the half-life, we know that half-life of a second order reaction, half-life is equal to 1 over K, the one that we derived. Half-life of a second order reaction, 1 over K A initial. 1 over Ka initial. That is the half-life of a second order reaction. So in this case, we need, since we do not have the value of the rate constant K, so we can determine the value. Okay, we can determine the value of K. So first we determine the slope. Okay, so slope is equal to, we know slope is delta y delta x. So in this case it will be delta 1 over C4 H6 over delta t. So we can pick first and last points. Okay, so which will give us 481. You can pick 481 minus 100 over 6,200 minus 0 seconds. So this one is liter mole. Okay, liter mole, since it is the inverse. It's the inverse of concentration. Okay, then now you can see the points that we have picked: 0, 100, 6,200, and this one. Okay, first and last. So we are going to find now slope is equal to, slope in this case is equal to 6.14 times 10 to the power negative 2 liter per mole second. Okay, so for a second order reaction, slope is equal to K. So that is our K. Then now half-life, we substitute now. Okay, so half-life is equal to 1 over K, which is the one that we have found, 6.14 times 10 to the power negative 2, okay, negative 2 liter mole second, then times the initial concentration. So initial concentration, which is equal to, when T is equal to 0, so from the table that we have, our initial concentration when T is equal to 0, that is 0.01, okay, 0.01 mole per liter. Okay, so you can see the units will cancel and we shall remain with the seconds there. This is more second, so then the rest will cancel. This will cancel with that. Okay, so now you multiply there and divide. So we are going to find the half-life as 6.3 times 10 to the power 3 seconds. So that is the half-life of this reaction. Okay, that is the half-life. Then the half-life of second order reaction is not constant as it is for a first order reaction. So it changes as time goes by. Okay, it's not the same throughout. For first order it's the same because it doesn't depend on the concentration. Okay, then the other reaction that we need to look at is the zero order rate laws. Okay, so most reactions involving a single reactant show either first order or zero order kinetics. However, sometimes such a reaction can also be a zero order reaction. Okay, so for a zero order, rate is equal to K A to the power 0. Okay, so A to the power 0, which will now give us it will give us K1. A to the power 0 is 1, which is equal to K. So for a zero order reaction, rate is equal to K. Then the integrated rate law for a zero order reaction, is A is equal to KT plus A initial. That is the integrated rate law. A is equal to negative KT plus A initial. Okay, then half-life of a zero order, half-life of a zero order reaction. So when we derive, we can derive, you know how to derive, you use the definition. Okay, so the half-life of a zero order reaction is equal to T half is equal to A initial over 2K. T half is equal to A initial over 2K. Okay, so zero order reactions are often encountered when a substance such as a metal surface or an enzyme is required for the reaction to occur. So metal surface, reactions which require metal surface, or enzymes. Okay, so most of these reactions are zero order reactions. Okay, so for examples, so if you have been asked to calculate the half-life of a zero order, this is the equation to use. Also, you can see clearly here that A is equal to negative KT plus A initial. It is also the straight line equation. So this is our Y, then this is mx, then this is B. So it means a plot of a concentration, this is T. This is T must give a straight line with a negative slope. Okay, this is the slope, negative slope. All right, so we can end here. Then next we shall look at the collision theory. Thank you.